In section 5.1, we talk about areas and distances and kind of the idea of how we get to definite integral, or why we have Riemann sums, or what actually is a Riemann sum, and how the old school mathematicians came to the idea of a definite integral. And then 5.2, it kind of connects the two, the Riemann sum to the definite integral. So I'd like to talk about those two sections kind of in combination and summary. The first thing to talk about is a Riemann sum. A Riemann sum is basically the sum of the rectangles that approximates the area underneath the curve. And you can see some of those rectangles here. So if we're talking about the area underneath this curve, this f of x here, graphed in red, and we wanted to look at the area from 0 to 4, from x equals 0 to x equals 4. And, well, bad picture, but we can pretend that they've divided this area into, 10 rectangles of equal width, and the width is delta x of the rectangles. The way we find delta x is to b minus a over n. So, you know what, we should move this line back here and say 4 minus 0, or 4 minus negative 1/2, or negative 1/8-ish, over n, which is 10. So the approximation of this area is actually a net area. You see that you're adding up these rectangles here, which are positive areas, and then these guys down here, which are negative areas. So when you do the definite integral, or when you add or you approximate the area under this curve, you're going to have positive area minus negative area for the net area, which is totally fine unless we're working in real life, in which case we'll take care of later. And probably section 5.3, 5.4 will take of how do we make that area positive. So a Riemann sum approximates the area. We use definite integrals to talk about area under a curve, to talk about distance traveled, and they can also tell us, they basically tell us the net change of a function over time, the net change of a quantity, especially if we're given the rate of change. So, for example, just for discussion's sake, if we're given a rate of change like a dV dt, a rate of change in volume over time, a dV dt is a derivative. If we integrate that dV dt, and this is a symbol for integration, right here, this kind of S, the reason they came up with this, Leibniz is the guy, because it looks like an S, like a stretched out S for sum, kind of, and a definite integral is actually a limit of the Riemann sum and comes from the idea of the sums of all these little strips, all these little baby rectangles. So if we integrate this rate of change, dV dt, integrate that, we're getting it from, let's say, from time equals 1 to time equals 2. We're going to get the net change in volume. Say we're filling up a cup and the dV dt is whatever rate you're filling up the cup with water. The integral of that dV dt is the amount, from 1 to 2, will be the amount of water, the volume added to the cup during that time from 1 to 2. So it's the net change. If you're also sucking water out of that cup with a straw at the same time that you're adding water to the cup, the net change is going to take into account that adding and subtracting. dV dt is also going to take that into account. So just a little idea about why we use integrals and how we use integrals and how they're useful. The other thing about Riemann sums to know, and I mentioned it already, I think, is that the definite integral is the limit as n approaches infinity. What that means is as the boxes, as the delta x, well, yeah, the boxes n is the number of boxes. So as the number of boxes gets larger, 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 larger to infinity, the delta x is going to get smaller and smaller and smaller. So as n approaches infinity, the number of boxes approaches infinity. The limit of this Riemann sum right here, circled in orange, the Riemann sum from I equals 1, I is the index 1 to n of f of x sub I. So whichever the x is, f of that x. So that's your basically your height of the box. And your delta x is your width of the box. So length, I guess, or height times width equals area of that little box. So basically the definition says definite integral is the limit of the Riemann sum. And in order to be integrable on that interval a to b, the function, this limit has to exist, which means that there can't be an asymptote in the area from a to b for this function. That's how we get our delta x. There can't be an asymptote in it. You know, a non-removable or an infinite discontinuity can't exist for a function to be integrable. Okay, here's an example from your book that talks about the connection between a Riemann sum and a definite integral. And I got a little bit of the solution in my picture there, so just pretend that's not there. So first, it says evaluate the Riemann sum for f of x equals x cubed minus 6x, taking sample points to be right endpoints, and a equals 0, b equals 3, and n equals 6. So basically what we're doing is finding the area under the curve x cubed minus 6x from 0 to 3. And I'm going to go ahead and graph that on my calculator. If you graph that, you see, and I don't really need to look at when x is less than 0 because we're looking at x equals 0 to x equals 3, but kind of this side looks over here. And then crosses through the origin, okay, we've got some of the points on the graph. So that x-intercept there is about 2.45, actually the square root of 6, where the graph crosses the x-axis, and this gives us a little bit of an idea of what we're looking at. So they want us to evaluate the Riemann sum by taking sample points to be right endpoints, and a equals 0, b equals 3, and n equals 6. That means 6 boxes. And taking the right-hand endpoint of the boxes, let me just draw. Let's pretend we're not taking the area in this area, but I'm just going to draw a box for you. If our intervals go like this, whatever, that's our interval. Taking the right endpoint of the box means this one, and then this one. So when we select our x values to calculate the Riemann sum, we're going to use the right-hand edge of our interval. Another way to look at it is on a number line, but first let's kind of do some calculations. If a equals 0 and b equals 3, then our delta x equals b minus a over n. So 3 minus 0, 3 over 6 is 1/2. Delta x is 1/2. So I know that each of my little boxes is going to be 1/2 in width. So I like to look at it along a number line because it's hard for me to see on the graph, and I'm thinking of boxes, and I really just need to worry about the width, all of those things. So from 0 to 3, my boxes are going to be here. There's one interval. There's another one. Go to 1.5. There's another one. There's another one. There's one. And there's one. We can look, and we have 6 boxes. 6 little interval areas. Let me clean that one up. 6 little areas. 6 little boxes that we're going to take the area of. They're longer strips, obviously. So when we look at these, we need to find our x values to be the right-hand endpoint. So here's a right-hand endpoint. Here's a right-hand endpoint. Here's one. Here's one. Here's one. And here's a right-hand endpoint. Do you see I have 6 endpoints? I'm hanging out on the right edge of each interval, the right edge of each box. And so that's what I want. That's how I choose my endpoints. If they ask for left endpoints, I'll mark those in blue. The left endpoints would have been here, then here, 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 here. There's your left endpoints. The only other thing they could possibly ask for is the midpoint of each interval. And that's easy to find, obviously, because it's the midpoint between. So here we'd be on intervals 1/4. The midpoints would be that in green. Anyway, but we're talking about the right-hand endpoints. So we're not worried about midpoints. We're not worried about left-hand. You see how some of this overlaps? We're only worried about the right-hand edge of each box. And that's going to give us our f of our x's to take an f, to take the function value of. So the Riemann sum, is part A of that, is going to be from I equals 1 to n. Our n is 6. And we're going to take f of x, which in this case is x cubed minus 6x. And we call those x sub i's, just so that they have an index on them. It would, if we were writing it in function notation, we'd say f of x sub I. Okay? And you'll often even see people call these sums the right-hand sum 6 r sub 6. The right-hand sum with 6 intervals is what that means. So, aside from notation getting in our way, we'll be all right. F of x, I, x sub I, and then delta x. Well, all we have to do now is evaluate each of those sums. So we got 1/2. That's our delta x right there. I just moved them in the front because I'm going to multiply that times every single f of x. Length times width. Remember that the delta x is the width. I'm going to multiply each of those, and so I don't need to do anything but just distribute it or multiply it at the end. So what are my x's? My endpoints here, my right-hand endpoints are these x's. The first one would be 0.5, then 1, then 1.5, then 2, then 2.5. I need a smaller stylus thing, and then 3. Those are the x's I'm going to put in for my x sub I. So f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3, all times delta x, equals the value of that sum. Okay? F of 0.5 is negative 2.875. F of 1 is 5. F of 1.5, excuse me, is about 5.6 or 625. F of 2 is 4. Negative 4, actually. All those were negative. We'll talk about why. F of 2.5 is 0.625. And f of 3 is 9. So we add all those up and multiply it by 1/2, and my answer is going to be negative 3.9375. How can an area under a curve be negative? Well, talking just mathematically here, this area under the curve that we took the area by approximating rectangles of right here is negative. It's below the x-axis. It counts as negative. So what you get, in effect, from a Riemann sum or a definite integral is what we call the net area. The net area means the positive plus the negative, or the positive taking away the negative area. If you wanted just all your area to be positive, what you would do is split these into two separate sums and take the absolute value of this area that ends up being negative. Okay, so that's what we get when we do the Riemann sum. The next part of the problem wants us to evaluate the integral, another thing that we can get some good practice on. All right, let's evaluate the integral from 0 to 3 of x cubed minus 6x dx. We're doing basic anti-differentiation is all that you've got to do with this definite integration added into it. So I'll give you the real quick rundown on how to evaluate a definite integral. You can find these properties. The properties are kind of the rules on page 307 of your text. If you don't have the text, let me know. I'll write out the rules for you. So we're going to first do the antiderivative of this. That's the easiest way. So we'll say x to the 4th over 4 is the antiderivative of x cubed minus 6x squared over 2. Now, when we did these before, when we did antiderivatives in section 4.9, we ended up with a plus c on the end. That is for indefinite integrals when you don't have these limits of integration here. When you have the numbers, the lower limit of integration and the upper limit of integration, you don't need to put a plus c because we're going to evaluate this from 0 to 3. And again, I'll give you the general definition of this on the next page. But watch me do it first. First, what we're going to do is evaluate this whole thing here at x equals 3. So 3 to the 4th over 4 minus 6 times 3 squared, right 9 in there, over 2. And then we're going to subtract the whole thing again, evaluated at 0. So 0 over 4 is 0. 6 times 0 squared over 2 is 0. So the answer here is 3 to the 4th over 4 minus 54 halves. If you work that out, we evaluate this and we get negative 6.75 for the area. Which is pretty close. I mean, we had, well, not pretty close really, but we used a lower estimate when we used those right endpoints. So we see that the Riemann sum isn't really as close to the integral as you'd like to get, and is in fact an estimate of the definite integral. We could get a good idea though of what the area might be using the Riemann sum. Here's the more formal definition of the definite integral. The integral from a to b of f of x dx is the integrated f of x, or the antiderivative of little f, which is big F, evaluated at b, minus the antiderivative of little f, which is big F, evaluated at a. And that's what we just did in the problem before this. Real quick, let's look at some properties of the integral. The constant multiple, if you're evaluating an integral from a to b of c dx, that's just a constant all by itself. So all you would have when you evaluate it is c times b minus a. That one's easy enough. You also could go ahead and integrate it and end up with c times x. So it would be cb minus ca. So you see how that works out. And the other one, the second property that we already saw demonstrated in that last problem, was that the derivative, the integral of a sum f of x plus g of x, and actually the same goes for a difference. The integral of this whole big daddy thing is actually the sum or the difference of the integrals of those individual functions. So like if it's a polynomial function, you have an x cubed and then an x squared. We'll let the plus and the minus be in there, so I'm going to write it twice. Then you can just integrate each little piece separately, which is what you do instinctively anyway, I believe. And then the third property that's important is basically the property that says, don't worry about a constant being multiplied by the function. It can just chill by itself. So if you have 5x squared is your function, 5 is your constant, it can pop outside the integral even if you want it to, and just let it hang out to the very end and multiply it by everything. Or you can let it chill inside the integral wherever you really want it to be. But some people really like to stick it out in the front just to get it out of the way. So c, again, is any constant. Well, I used 5. I was thinking about 5 and I wrote it. C. That constant c can pop out to the front. There's no specific c, it's just random constant c. So there's some important properties of integrals. Here are some exercises that involve these concepts.